So final section of chapter 4, we're just going to be looking at some word problems and setting a few things up here. So in this first one, they are describing this parade, big giant floaty penguin up there attached to some cables, keeping that thing from blowing away. So it talks about the two cables that we're seeing make an angle of 48 degrees and 40 degrees with the ground. And that's important as well. Make sure you notice those little phrases like this one, where it said with the ground. So that helps tell us where to draw it. Obviously, the larger angle would be the 48 degrees, and the smaller angle would have to be the 40 degrees. So they're giving us that information. It says a little later on that they are 10 feet from each other, so that's where the 10 came from. They're asking ultimately, how high is the penguin above the ground? So we are solving for h. But they did not give us a value here, so it's not quite the straightforward right triangle problem, but just a little more side work to get us there. So first things first, the main idea is we're essentially seeing two variables, right? I don't know what this is, and I don't know what this is, and typically when you're doing math problems and you have two unknowns, you need two equations to solve. So that's kind of what we're looking at with this one. So we'll just start with this inside triangle right here, and we'll do a tangent function. So if we said tangent of 48 equals h over x, that's going to set up the first equation for us. So we got that guy, and now if we looked at the other one, so from 40, so if I was going to talk about the tangent of 40 degrees, if I did opposite over adjacent, opposite is obviously still h, but what about the adjacent side? So if I look at all this, total, I'm looking at x plus 10 for my adjacent side, so we're going to say h over x plus 10. So we have our two equations, and we're just going to use a little substitution here in order to figure out our height. So for these guys, so just with the way that these two equations are set up, it's going to make the most sense to isolate the h, sub him out, and then once we figure out x, we can then just plug that back in to figure out what our h value is. So for this guy in both, I'm going to take the denominator and multiply it over to the other side. So on the first equation, we're going to figure out that h is x tan 48. All right, so that equals h. If I isolate this h by multiplying that x plus 10 over to the left, so if they both equal h, by substitution, they both equal each other. So I can set those guys equal to each other and say x plus 10 tan 40 puts us right here. So we're going to get our x's onto the same side. Before I can do that, I have to distribute. So I got my x tan 48 on the left. A little distribution over here. I got x tan 40 plus tan 40. And realistically, angles like 48 and 40 are not angles that we would deal with without a calculator, right? Those aren't like 30, 60, 90, 45, 45, 90, none of that stuff. So since those are numbers that would really require a calculator, really at any time, you could convert these into decimals if you felt like that was easier for you to do. Typically, they don't like us to use the calculator until the very end because they want us to keep numbers as exact as possible. So that's kind of the goal. So I'm kind of doing the same thing. But like when I see something like 10 tan 40, that's just a number. I could type that into my calculator and change that to a decimal if I really wanted to. But I'm going to hold off until the end, just like they do. So anyway, I'm going to get my x's onto the same side. So I'm going to subtract my x tan 40 over. If I can give myself a little more room here, so x tan 48 minus x tan 40 equals my 10 tan 40. So we're here, so the whole purpose of that was so that we could now factor out x as a common factor. A little trick we've used before. So we're here, and then one last step would be to take this and divide it over to the other side, and that'll tell us our answer for x. And this is where we'll throw it into the calculator and get a value for x. Ends up being about 30.905 if we round that. I'll try to go as deep as I can because we're not done yet, right? We're solving for h, so really I don't want to simplify my answer too far before I'm done with the problem. So even if I was doing this, if I had my calculator in front of me, as I go to plug that back in for x, in order to simplify it, so remember this equals h, so all I have to do is take my answer for x and plug it back in. So while this is still on my screen, I would just hit times tan 48 and get my answer from that. All right, so that's all you'd have to do to finish that one off. Well, let me flip over. Hold on, I got pages stuck together. There we go. So we take you down to this guy. So here was, again, I was trying to save you some writing on this. I just kind of turned this into a fill-in problem so you wouldn't have to write all this stuff down. So on this one we have a patrol boat leaves port at 35 knots, miles per hour, so that's its speed, for 2 hours on a course of 55 degrees, and then 3 hours on a course of 145 degrees. So what are the boat's bearing and distance from the port? So we've talked about these bearing problems before, so this will look hopefully a little familiar to you. Remember that when they just say something like 55 degrees, that is 55 clockwise from the north. And so for this one, let's set up our little angle. I'm just trying to make sure I draw this to give myself enough room here. And then we're going into course of 145. So I'm going to go start right about here. So here's our boat. That's my boat. So here is our compass that we are starting with. So if this boat is going to travel 55 degrees clockwise from the north, that would put him about here. So here's my 55 degree angle. If it was for 2 hours and he's going 35 nautical miles per hour for 2 hours, right, that puts us up to 70 miles. So that would be our length of that segment right there. From there, now he's going to change course, and for 3 more hours, so if I do 3 times this, that's going to give us, what, 105 miles for the next length. So it's going to be a little longer than that guy. But this one's at a course of 145. So remember that is 145 from the north, from where he's at now. So here's my new compass. So here's 90. Halfway through the next part would put me at 135. He's going 145, so I'm going at about this angle right here. So I'm going to go with that. So again, this was my 90 right there, plus another 55 degrees in order to make it 145 total. So that was my 145 degree angle. So again, this is 55 right there. For 3 hours at 35 knots, so we're looking at 105 miles right there. So ultimately they are asking us for the boat's now distance from the port. So this segment right here, we got to figure out that length. We are also looking for the boat's bearing from the port. So we got to figure out that angle as well. So here is the length that we are now looking for. So we got to figure out that one. We also need to figure out the angle from the port. So in that sense, remember, here was the port, here was the bearing. So if we measure it from the north and go clockwise, that means I am looking for this angle right there, right? Because I got to go clockwise from the north from the port. Is kind of what it's describing for us. So I'll kind of mark that. So that's the bearing that we're trying to come up with. So from the drawing that we have, we need to come up with a couple more angles. One thing they need us to see is that this, if we do the math, is a right angle. So I have a 90-degree angle right there. Here is why. A couple ways you could have figured this out. If you look at this northern line, which is parallel to this northern line, I do have some alternate interior angles right here. So in other words, if that's 55, then that's 55. I already know that this is 35 because, again, I had a right angle here. Right? So if I subtract that out, this is 35. If that's 55, that gives me my right angle right here. So here's a couple approaches you could take to get there. That's just sort of one idea, but we do need to identify that guy as being 90 degrees. So we do have a right triangle, which makes life a whole lot easier on us. So let's just fill in a couple things for what they gave us here. So AB, so they're calling this AB, is 70. We're going to get from B to C is our 105. So let me label the way they labeled. So we figured out our 70. We figured out BC is 105, and we need to figure out the length of AC. That was one of the things they asked us for, is how far the ship is from the port. So you can see on that one, we can now use Pythagorean theorem now that we know that it's a right angle. And so that's where this math came from, just a little Pythagorean theorem. Figure out it's 126.2 miles. So that was one of the things they asked us for. Let's see if we can come up with our bearing on. As we break apart this angle, obviously from here to there we already know is 55. So we just need to come up with this interior angle of this triangle so that we can add it on to 55 and get our answer. So they are calling this interior angle our variable. That's theta. So how do we come up with that? We can use a little inverse trig now that we know all of our side lengths. So I would go from, so if I'm going from here, I don't really want to use my rounded answer that I got earlier from Pythagorean theorem. It's better to use values that they gave us. So I'm going to use my tangent and do opposite over adjacent. So the tangent of theta, I'll do this off to the side here. So my tangent of theta is going to equal opposite over adjacent. So we're going to do inverse tangent of that ratio right there. Let me throw that into the calculator. Make sure I am in the world. Make sure I'm in degrees. That's important. So inverse tangent of 105 over 70. So 56.3-ish for theta. So there's that angle. So now I can kind of finish this thing off and do my 56.3 plus 55 to get my complete bearing that we were looking for. And so that's what they did right down here in the final stage, is they added the 55 to what we just got in order to get the total value for the bearing. All right. Let me move on. So before we see this next guy, we're going to take a peek at page 384 of your textbook. Let me pull that up, and then we'll get going on to this one. So a little bit that they talk about with our harmonic motion that we're going to be doing on this one. So this has to do with the motion of something almost like bouncing up and down, right? But if there's no resistance on it in any way, it can keep going up and down with the same amplitude again and again and again and again without losing any of its height or depth as it goes up and down. So one of the things that gets thrown into this Obviously, with something being periodic, going up and down, like an amplitude, we can fit this into a sine or cosine function. But here's like the one little extra piece. See the little W that they have right there? That's basically our B value that we've used before, always affected by the period of the graph. One of the things that harmonic motion talks about is the frequency, which is just the number of oscillations per unit of time. So on this guy, they do identify frequency as the reciprocal of the period. So if I know the period, I can flip the period upside down and call it 1 over the period to get my frequency. We will still find this value the same way that we always have. If this is like our B value, we've always used period is 2 pi over B. Still true about this, even though it's a W instead of a B, we're still going to take that same approach. So let's take a look at what's going on with this one. So first things first, in this one I do have, remember we have the choice of choosing our sine function or a cosine function. And usually what would determine which one you would use is, does the item start at the amplitude? Like, does it start at its highest or lowest point? That would be a cosine function. Or does it start like at 0, right, in the middle of the oscillation? So if it's starting at 0 in the middle, then I definitely want to use a sine function, as you kind of can draw back on our parent functions of sine and cosine graphs to see why we would choose that. So in this case, this one, we're just starting in the middle at 0. It's going to go up 5. It's going to go down 5. So that's our amplitude that we're seeing on that one. So we know our A value is going to be 5. Here was kind of the extra piece to this. So you can already see where they got our A value of 5 based on the amplitude of this. So for this one, they said that it takes 3 seconds to complete one cycle, right? 3 seconds to complete one cycle. If you were asked for the frequency, I can take that 3 seconds, flip it upside down, and here's my frequency, right? So that's how we would identify the frequency. This I felt was a little more confusing than it needed to be. Really, all we're doing is going back to our basic formula of 2 pi over B, or in this case W, which is like in the position of B, in order to get the period of the graph, right? So they told us on this one that the period is 3 seconds. So I'm just saying 3 seconds equals 2 pi over W. If I multiply my W over to here and divide the 3 back underneath, just like we've done before with our B values, then we got our value for W. And so that gets subbed in right here, just like our B value would, and we have our sine function. So not too bad on that. If you need to see more information on the harmonic motion stuff, there's another example in the book on that page, on page 384, so you can always look at that further. But really, that's the base of it. It's just really just finding a sine or cosine model and just plugging in using the period as well as the amplitude to get a function for it. But that is it for chapter 4.